Assalamualaikum and good day everyone. So we will continue with week 14 of the lecture, which is about a register. You can get the slide from the e-learning. I will teach again using the module because not all of you have the module, and of course the module is more complete form, and I will not read word by word, okay? I will do summarization. If I do word by word, the video I believe will be even longer, okay? So we go to page 153 for the register, okay? Okay, so this is the page, okay? So two main applications of flip-flop are registers and counters, okay? So you learn already flip-flop and counters, right? Now we are going to learn flip-flop for register, okay? So register are used to store multiple bits of data, okay? By the name you know already. Shift register are used either to delay data or to serialize or deserialize parallel data. Counter are used to count event, okay? Just like we learned in the previous lecture. This chapter focus on register and shift register. So please understand this point, okay? Used to store multiple bit of data, used to delay data, or to serialize or deserialize parallel data, okay? So data register. Data register, also known as storage register or simply as a register. So you can have either of these two names, okay? Either storage register or a register, okay? It's a set of flip-flop connected to store a bit in each flip-flop and control as a unit. So it have a flip-flop in it. They use flip-flop, okay? So you have to understand about this. Application of the storage include temporary storage between a counter and a display, intermediate storage between component of arithmetic units, and various types, okay? So a simple of 4-bit data register is shown in figure 2.1. You see this mentioned 4-bit, right? So you have 4 flip-flops, okay? A timing diagram illustrates the operation of the data register is shown in figure 12.2. We will go to there later on. This diagram introduces the concept of signal groups. Okay, when several signals combine to form a numerical value, the combined value is shown as a single bus signal. Okay, the numeric value can be written in, of course, binary, decimal, octal, or decimal notation. Okay, I don't know. This is double typing. Okay, so it's okay. So from this diagram, okay, here we can also see that a data register sample the input data D320. So this is your input data. Okay. On the rising edge of the clock, okay, you see this is your rising edge of the clock. Okay. Also here, okay. And hold it on output Q30. So this is your output, okay, until the next rising edge. You see, so this is the next rising edge, this is the next rising edge, and this is the next rising edge, okay. Data to be stored in register must be maintained until the clock edge arrive, okay. So it will restore the data until the next clock edge arrive. For example, whether it's a rising edge or falling edge, okay. Any changes in data input before the clock edge are ignored, okay. If you see here, this is your 0010, okay. When it is at the rising edge, okay, only then you see we have some changes, okay, which is 0010 here, okay. And then from the word here, any changes in data output before the clock edge are ignored. Okay, if you see this is our clock edge, okay, you see there is changes in D320 before the clock edge. So this is ignored, okay. We only take consider the input when the clock edge arrive. Okay, like for this one. Okay, this clock edge arrive. So this why 111. So you have 11 here for your output, for example. Okay, you may have different combinations, but I hope you understand the concept. Okay, so that's why intermediates this before the clock edge, we ignore them. So shift register are flip-flop connect such that data loaded into flip-flop is fed to another flip-flop in the sequence on the arrival of a clock pulse. Okay, so data loaded into a flip-flop is fed to another flip-flop. Okay, so flip-flop to another flip-flop in the sequence of the arrival of the clock pulse. Shift register useful for delaying data and for converting data from parallel to series or vice versa. Okay, 4 classes of shift register exist. Okay, so we have this name: CISO, SIPO, PISO, PIPO. Okay, I think this one is very straightforward. Like this: serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Okay, so my voice may be not really not really that loud. Okay, because now it's 1:04 a.m. Okay, people are sleeping. Okay, so let me go one by one. Serial in, serial out. I think this is very understandable. Okay, data is shifted in and shifted out serially 1 bit at a time. We'll see the next figure. Okay, here. Okay, serial in, parallel out, data is shifted serially and flip-flop outputs are readable simultaneously because it is parallel. That's why simultaneous. Parallel in, serial out is all flip-flop inputs are loaded simultaneously because parallel, and the data is read 1 bit at a time. Next, parallel in, parallel out. Data is read in and read out in parallel format or serially. Okay, so now for better for better visualization, okay, you see here, this is your serial in and serial out. Okay, so this is your clock pulse. Okay, I think you guys already familiar, right? This one is actually clock pulse. Okay, so you see this is serial in. Okay, and you see there is one series data in, another series data out. So this is serial in, serial out. Okay, next we go to SIPO, serial in, parallel out. You see one data serial in and you have multiple output simultaneously. So this one is serial in, parallel out, simultaneous. Okay, this one is parallel in, serial out, means here you can see data inputs simultaneously and you will have a serial data out. Okay, one data out. Next is PIPO. You see you have simultaneous data in, then you have simultaneous data out. Okay, and of course of all of them, you see the common feature is what is they have clock. Okay, they have clock pulses. Okay, so this is data movement in your shift registers. Okay, now figure 12.4 here and 12.5, this one, show the logic diagram for CISO and SIPO shift register respectively. So this is your CISO and this is your SIPO. Okay, table 12.1 show how the SIPO register work. Okay, this one later on when we go to the next page. So you see this is the flip-flop. Okay, and you can see series data in and series data out, one in, one out. How about the SIPO? You can see you have one series in and you have multiple output simultaneous. Okay, okay. Okay, now we go for the timing diagram. Okay, so timing diagram of the SIPO shift register operation. This one is serial in, parallel out. Okay, so serial in, parallel out, this configuration. Okay, one in, parallel out. Okay, So if you notice, okay, this is your serial data in, serial data in. Then you have this as your data output, A, B, C, D. Okay, you see at the first clock edge, okay, your first flip-flop will have a change in output. Okay, however, flip-flop B, C, and D, not yet. Then at the next rising edge, second, okay, you can see the B start to have a change in output. Okay, so but C and D not yet. Okay, and then at the next rising edge, only then this flip-flop C will have a change in output. Okay, and same goes for the last flip-flop D. Okay, where you have changes in output for flip-flop D. Okay, you can see it's like in pattern. Okay, so this is serial in, parallel out. Okay, so behavior of SIPO shift register in tabular form. So this is just like what I'm explaining here. Is just put into a table. Okay, so you see there is a clock. Okay, 0, 1, 2, 3, 4, 5, 6. So 0. Okay, this one they use a lot. Okay, so this one is the clock. Okay, so this is the A, means the next output. Okay, you can see, I think you know already, right? What does it mean by plus here? Okay, so in easy understanding, you may relate with what I explained with the table. Okay, you can go through one by one and you try to see. Just like this, for example, at the early clock, your input is 1. Only your output have changes is in output, just like what you see here. But the rest is still 0. Okay, so I think you can get right. So the rest is also the same. Don't be too rushed in study. Okay, you need to see line by line. Okay, I can go one by line, but then the video will be longer, and of course I read you, some of you may dislike longer video. Okay, so I cannot satisfy everyone, but I try my best. Okay, the basic SIPO shift register will shift its input every clock cycle. This is just like what I explained. Okay, so this one is actually the same as what I explained. So this one in a word. Okay, this one is I already explained in my own sentence. Okay, so by using a big, this one you can replay my explanation. Is actually about this one. Okay, by using a bigger multiplexer, the input to each flip-flop can come from more sources, including from external source. I think this one you agree, because we learn cascading and many things, right? In order to have a bigger combination, something like that. Okay, this is how parallel data can be inserted into register, which are necessary for PSO and PPO type register. Okay, so by using bigger multiplexer, the input to each flip-flop can come from more sources. Okay, means we can have more input. Okay, if we use bigger multiplexer, this is how parallel data can be inserted into register, which is necessary for PSO, PPO. You see, parallel in, for both parallel in condition, but can be serial out or parallel out. But this one is especially for parallel in. Okay, if you want to have more parallel data input. Variation of the individual flip-flop inputs allow different modes of operation. Okay, as can be seen later in 74 times 194 device. Okay, so it says later, so never mind, later. Okay, so this is the shift register operations. Okay, this pretty much explain what I explained in the figure 12.6. okay, here and here I think is almost actually explaining this in different way. Okay, you can see the movement. Okay, just like you see what happened in the timing diagram, and you see this is the changes in output. Okay, finally at the last output D. Okay, So you can see the pattern they shown you, just like the timing diagram. Okay. Now figure 12.8. Okay, a SIPO serial in, parallel out. Okay, with shift enable control input. Okay, you see you have shift enable control input. So what is this? If you guys remember, this is what? This is, what is this thing? If you able to guess, okay. So this is a multiplexer, am I correct? Okay, I think this is a multiplexer. Okay, so you can see, okay, we have enable control input. Okay, with shift enable control input, so you can have 0 or 1 here. Okay, if you have 0, what it will take, what it will choose. If you have 1, what will choose. So I leave it to you guys to recall the multiplexer lecture. Okay, and of course you can always refer to the lecture video. Okay, and this will help you to understand the function of the why we include multiplexer here. Okay, so this is a SIPO shift register with shift enable control inputs. Okay, so here you will see your input can be varied. Okay, your input can be varied, whether it is affected by, okay, it is due control by the shift enable, and also you see because it's multiplexer, it can be affected, associated with this or this before it's going to here as your output. Okay, and you can see there is a loop back there also. Here there is a loop back. Okay, so I hope you don't too rush. Okay, try to, because this will take your understanding from multiplexer and also the previous chapter on the sequential. Okay, so take your time in understanding this figure. Okay, now we go for the 12.3. Okay, so the 74,100 logic family has integrated circuit performing data register and shift register function. Several are listed in table 9.1. Okay, so this one you can see on the module. Okay, but never mind, I just show first here because I know not all of you have the module. Okay, I try to be understanding on this matter. Okay, that's why I'm teaching on the using module video. Okay, so I open first. Okay, table 9.1 here for you, for the one that didn't have the module. Okay, I help you guys to search for it. Okay, wait for a while. Okay, so the 74 logic family has integrated circuit performing data register and shift register function. Several are listed in table 9.1. So this is your table 9.1. Okay, so this is your table 9.1. You can pause the screen to see. Okay, now we continue. Table 2.2 shown the register device from the 7400 logic family. So you have 74 times 91, 8-bit SISO, 8-bit SIPO, 8-bit SISO parallel in serial out, 8-bit SISO PISO, 6-bit data register, universal shift register, and this is the pin number. Okay, how many pins do you have? This is the chip number. Okay, so I believe I will not cover all. Okay, I will divide this lecture to two parts. Okay, so we try to go some but not all. Means later on you will have a second part of the register. Okay, now the 74 times 174 device. implement a 6-bit data register. Okay, obviously you can see there is 6 bits. Okay, 1, 2, 3, 4, 5, 6. You have 6 bits. Okay, this device has a data input D is stored during a 0 to 1 transition on the clock input. You see, is stored, data input is stored. Okay, sorry, data input is stored during 0 to 1 transition on the clock input. So you have clock 0 to 1 transition. 0 to 1 transition. Okay, data is stored. Okay, is stored. Okay, for 74174. Okay, so I don't want to, because not all of you want to have the module, so I don't want to do too many doodle or sketches here. Okay, so this device has a synchronous MR master reset. Okay, so master reset, this is master reset. Okay, if it's active low, okay, if you have a 0 here, it will be reset. I think you guys already familiar with this. Okay, and this one, if what kind of flip-flop is this? Okay, so this one I leave it to you. Okay, for to see on the previous chapter, okay, what flip-flop is this? Okay, but if you see here mentioned D, so what? Try to guess. Okay, D, and this one is flip-flop. So what flip-flop is this? Okay, so this is the logic symbol for 74 times 174. So this is basically the basic representation of 74 times 174 register. Okay, so you have D0, D1, D2, D3, D4, D5. This is actually your input. Okay, and this is actually your output. Okay, so if you notice here, okay, try to guess what is this. Is this CISO, SIPO, PISO, or PIPO? Okay, you see, you have several data input and you have several data output. So what do you think it is? Is it CISO, SIPO, PISO, or PIPO? Okay, what is this? Okay, just I try to for you to help your mind to brainstorm, to think. Okay, and I think this is not really difficult question. You can see already. What is it? Is it serial in, serial out, serial in, parallel out, parallel in, serial out, or parallel in, parallel out? Okay, so next we go for 74 times 165 device. Okay, the 74 times 165 device is an 8-bit. Okay, 8-bit. Okay, let's we go for this. Okay, an 8-bit. 74 165 is an 8-bit CISO, PISO. Okay, CISO, PISO. Okay, so it can be either CISO or PISO. 8-bit parallel to serial shift register. Okay, it is commonly used to exchange data serially between microcontroller. Okay, between the micro C. Okay, the 74 times 165 has the following connection. We have serial in, we have parallel input P0 to P7. Okay, mind the word parallel. Okay, and mind the word here serial. Okay, clock signal CLK through 2 pins. Shift mode SH LD, low to load, high to shift. So if it's low, it will load, and if it's high, it will shift, do the shifting, and you will have serial data output. Okay, Q0 to Q, it have serial data output Q7 or inverted Q7. Okay, you see the inverted here. Okay, so let me erase so that you guys, those that didn't have module, able to see it clearly. Okay, now the two clock pins are identical but are usually used in this way. Okay, they are identical. Pin 2 is for the actual clock and pin 15 is the clock inhibit. So you have the clock, you have pin 2 and you have pin 15. Pin 2 is actually for the actual clock, the real use for actual clock. Okay, and the pin 15 also the clock pins, however it is used as a clock inhibit. I think there is figure later on we see. Okay, when the clock input inhibit input is high, okay, you see, if the clock inhibit input is high, which is 15, changes on the clock pins are ignored. Okay, means if clock inhibit is high, it will ignore the clock pin, the 2. Okay, and the shift register hold the previous value. When this one is high, okay, the clock pin is ignored, and also the shift register will hold the previous value. I mean, it will not, it will maintain whatever value that they have previously. So refer to figure 12.1 and table 12.3. Later on we will let's see. Data is loaded into the shift register through the parallel input. Okay, when sh/inverted LD is low. Okay, so data is loaded into shift register. You see, low to load. Okay, low to load. Data is loaded into shift register through the parallel input when sh/LD is low. That's why this is explanation. Okay, low to load. Data is shifted in from the serial input pin when sh or LD is high. You can see, if this is high, it will shifted the serial inputs, this one. Okay, which is, this is your parallel. Okay, it will shift it if this one is turned high. Okay, because if it's high, it is shifting, and if it's in LD low, it will load the okay, it will do the loading. Data is shifted out from Q7, which allow multiple devices to be cascaded. Okay, so we go to see figure 12.11 and table 12.3. Okay, where is it? Oh, okay, here, sorry. So this is your figure 12.11. So you can see pin 2 and pin 15 is clock. This is the actual clock, but this is the clock inhibit, just like we see the operation. Okay, when the clock input inhibit is high, what happened? Okay, it will ignore the clock pin. Okay, and shift register will hold the previous value. If you see, okay, P0 until P7, this is all our parallel data input. Okay, and this is our serial serial input. Okay, serial input, serial input SER pin. Okay, and this is our data outputs. Okay, data is shifted in from serial input, okay, when sh/LD is high. Okay, so it have two conditions. Okay, low and high. You need to see it. Okay, okay, so you can pause the screen for those that don't have the module. Okay, now we see the table 12.3. We try to see from figure 12.3. Okay, so this is your table 12.3 truth table for 74165 shift register. Okay, I make sure this is correct table. Okay, so you have function. If you want to hold the previous value, okay, this one what you need to do, and this one what you need to do. If you want to do right shift, what you need to do here, and parallel what you need to do here, and what you see observe as the next step. Okay, so we can go one by one. Okay, so okay, so here SHOLD whole, it is whole. Okay, so it hold the previous value. Okay, let we see from our understanding last time. Okay, when the clock input is high, changes on the clock bit are ignored and the shift register hold the previous value. So this is what happened. Okay, so it hold. Okay, we hold, and clock input is high. Okay, so it will maintain the previous value. That's why you see the next step, you have Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. It maintains the previous value. Okay, sorry, okay. Then how about if you now you have starting to have shifting, a right shift. Okay, if you have right shift, okay, you have set this one to high. Okay, then what happened to clock inhibit? Clock inhibit turn low. Okay, now we go for we just see from the previous page. Okay, okay, when the clock input input is high, changes on the clock is ignored and shift register hold the previous value. This is what when it's high. So when it is low, okay, so what happened when it is low? Okay, so if it's low, then we will follow the clock. Okay, then we will close the clock, means the clock will not be ignored. Okay, the clock will not be ignored. So what happened is that you can see the next step. Okay, when you have this as high and clock inhibits is low, it will follow the, and then the actual clock, which is the pin 2, will be considered, and you see your Q0 plus, okay, will take the value from the SER, okay, which is here. Okay, data is loaded into the shift register through the parallel input. When SHLD is low, data is registered from the serial input. Okay, when SHLD is high. Okay, so data is shifted. So when SH and LD is high, okay, clock inhibit is low. Okay, and means that the clock will not be ignored. The actual clock, it will be considered the pin 2. That's why it loaded the serial. Okay, it loaded the is shifted in from serial input SER pin. Okay, sorry using the word load. Okay, is data shifted from serial input SER. Okay, however, at this stage we still have this Q0 maintaining sorry, not maintaining, because it's shifted, so you have the shifted. Okay, Q0, Q1, Q like this, Q3, Q4, Q5, Q6. Okay, it will be shifted. That's why the name shifted. Okay, okay, data is shifted out from Q7, which allow multiple devices to be cascaded. Okay, now next is if we want to have parallel load. Parallel load, what we do, we set this HL or LD to be low. Okay, you see, we set it low. What happens if we set it low? Low to load. Okay, low to load, and data is loaded into shift register to parallel input. Okay, here when SHLD is low. Okay, so you can see this is low, so it will consider the parallel input, and clock inhibit will not be considered. Okay, either high or low. Clock as well, because at this time they are receiving the parallel input. So you can see Q0 plus P0, Q01, Q1 is P1, and so on. This is the parallel inputs. Okay, I hope you understand. Okay, next we go for the 74 times 194 device. Okay, the 74 times 194 device is universal shift register that can be used as either serial to serial, okay, serial to serial, serial to parallel, parallel to serial, left shifting, right shifting, and as a parallel to parallel data register. It requires extra control input to specify the desired function. Okay, the 74 times 194 has the following connection. Okay, serial input, which is can be from your LSI and RSI, parallel input, which is your DCBA. Okay, DCBA. This is your serial input. This is your parallel input, because you can see it can perform many functions, right? Then you have parallel input, which is here, QD, QC, QB, QA, and you have clear signal. Clear signal here. Okay, and you have input S1, S0, which determine your shifting function. Okay, you see here, this is function table for 74 times 194 shift register. Okay, so you have this function, okay, because it can perform many functions, right? So this is to function for hold, function for shift right, function for shift left, function for parallel loads. So you can see this is your input S1 and S0. So you see, because it's S1 and S0, you have 4 possible combination. Okay, so if 0, 0, it will hold, 0, 1, it will shift right, 1, 0, shift to the left, and this one 1, 1 will consider parallel loading. Okay, so hold, it will just hold. You see, it just hold the previous value. Shifting right, you can see RSI comes in first, then QA shift, everything shift to the right. How about shifting left? Then you have LSI here, and your QD shifted to the left, QC, QB. Okay, I think you can relate. Now parallel load, what happened is that it's going to start receiving parallel data in for S1, S0 equal to 1, 1. Okay, A, B, C, D. Okay, so this is this is example of a 4-bit ring counters, okay, which will be covered, okay, in the next lecture. Okay, so we will finish this chapter register on Johnson count on the remaining, okay, 2.4 in the next lecture. Okay, so with that, assalamualaikum, and see you next time in the next lecture. Good night.